Greetings, my name is Rosalío Reyes and I am going to talk about of my work, geometric and topological properties of the complementary prism network. This work is on collaboration with Jesus Méndez and José María Cigarreta from Universidad Autónoma de Guerrero, Mexico, and José Manuel Rodríguez from Universidad Carlos III de Madrid, Spain. Given a graph G, we consider its complement, dented by overlap G. We can think of the complementary prism of a graph as a kind of product between the graph G and its complement, in which we add edges between vertices that correspond to each other in the graph and its. Therefore, we can also see it as an operator on a graph G. First, we analyze the geometric properties. For this, we use the concept of hyperbolicity in the sense of grammar. We can consider a graph as a metric space. For this, in addition to the vertices, we consider the internal points of the edges. The distance between 2 points is the length of the shortest path connecting these points. This path may not be unique. Let's just consider a geodesic metric space. In this space, we take a geodesic triangle T. We say that T is delta sin if each side of the triangle T is contained in an environment of size delta of the union of the other two sides. We have the following examples. Every tree with edges of arbitrary length is zero hyperbolic. The reason for this is that no matter where consider the three vertices of our triangle, when considered the union of two sides, we have that the third side is contained in this union. In the case of Rn, we have that the space is zero hyperbolic if and only if n is equal to 1, for the same reasons as the previous case. If n is not equal to 1, the space is not hyperbolic. Since no matter what size of delta we chose, we can always find a triangle with sides out of the delta size environment. Any bounded metric space is hyperbolic. A useful delta is half its diameter, but we usually look for the optimal bounds. Riemannian manifold with certain characteristics are another example of such a space. The open unit disk D with its Poincare metric is hyperbolic. Among the most prominent applications are the graph that models the routing of Internet, secure transmission of information through the network, spread of virus, and the DNA study. Furthermore, the study of hyperbolic graphs is important because the hyperbolicity of many metric geodesic space is equivalent to the hyperbolicity of the graphs associated to this space. Let's just now turn to the analysis of the complementary prism in this perspective. The first result shows us a hyperbound for the hyperbolicity of the complement prism. The idea of the proof of this result is the following. First, the diameter of vertices of the complementary prisms is less than or equal to 3, and considering a well-known result, we obtain the mentioned theorem. The following result shows a bound relating the hyperbolicity constant of the original graph, its complement, and the complementary prism. A more specific result than the previous one is the following. Note that here the bound depends on the diameter of vertices. In general, when consider connected graphs, the diameter of vertices is the parameter that gives information about of the hyperbolicity of the complementary prism. For the case of the diameter of vertices is equal to 1, we have the following result. This result has the following consequence. Here we have the constant of hyperbolicity of the complementary prism for the complete graph K sub n. The next case is when we have the diameter of vertices equal to 2. In this case, we have a lower and upper bounds. The next case is the diameter of vertices equal to 3. Same as in the previous case, we have a lower and upper bounds. The following result is very similar to the previous case. Now we study the case when the diameter of vertices is equal to 4. Finally, we have the case when the diameter of vertices is greater than or equal to 5. In this case, we have that the upper bound is reached for every network with this diameter. All the previous results can be summarized in the following result. We also have the following result. Subsequently, we consider disconnected graphs. In this case, this diameter is the diameter of vertices by removing edges connecting vertices of degree 1. Let us now turn to topological analysis. A single number representing a chemical structure in graph theoretical terms via the molecular graph is called a topological index if it correlates with a molecular property. Topological indices are used to understand physicochemical properties of chemical compounds. Topological indices are interesting since they capture some of the properties of a molecule in a single number. Hundreds of topological indices have been introduced and studied, started with the seminal work by Wiener. An example of a general topological index is the following. We consider a graph with n vertices and asymmetric function A. Then we consider the general topological index A and A reduced, defined by here d sub b is the degree of the vertex B. With this definition, we have that the index applied on the complement of G is given by this expression. And we have the following results for the complementary prism of G. Note that in this case the function A is symmetric and takes two positive integers values. The next index is based on a function which takes only one positive integer value. As in the previous case, we have a general topological index and a reduced index B. Note that the index B can be written in the following way. Now we apply these indices to the complementary prims of a graph and we get an interesting result is to consider the function b as an increasing or decreasing function. If b is an increasing function, then we have The Wiener index was proposed in 1947 with the idea of introducing the topological concept of distance and used it for the characterization of the branching of a molecule. We can consider a generalization of this index as follows. Note that if lambda is equal to 1, then we have the classical Wiener index. Some results obtained for this index and the complementary prints of a graph are the following. First, for the case when lambda greater than 0. If lambda is negative, we have and that's all for the moment. Thank you very much.